Hi, welcome to this video. My name is Zacharias, and together with Laura del Toso, we'll be giving you a short introduction on deep learning frameworks for medical imaging. Before talking about deep learning frameworks, we can talk about environments and what you can use. So MATLAB is a very popular environment that can be found in most universities and laboratories. And lately it comes with a deep learning toolbox, which can be used to actually implement machine learning and deep learning models, test them and use them in the MATLAB environment, and can also be used to import projects from other environments as well. But it's not the environment we would recommend for beginners that start from scratch, unless they heavily rely on a project that's already been developed in MATLAB, because it's not used a lot by the general community, so there won't be a lot of help you will be able to find online or projects that you can use to as templates to build your project upon. Instead, the use of Python has been growing exponentially over the years, and there is many packages online that can be used for scientific and for imaging tasks. And also there are machine learning frameworks as well that can be used with Python. And it's quite easy to install, and it supports CPU and GPU computation, which can be quite important. And it's very heavily used by the general community, so that you will be able to find a lot of help online or projects to compare with yours or use as templates for you to start your own project. An easy way to install Python and actually manage all the packages is Anaconda, which comes with a number of commonly used packages pre-installed, and you can use that to manage your packages and also virtual environments which you might want to use for different projects. And one nice extension you can include for Python is a Jupyter Notebook, which gives you this nice framework where you can have your input and your output laid out, and you can annotate your code, so it will be quite nice for showing your project to others or sharing your project online, but also for you to be organizing your project and the steps in your process. So now moving more on the deep learning frameworks. The most popular library used is Tensorflow, which is really the backbone for building machine learning models. And together with Keras, which is now included in Tensorflow, it's relatively easy to, with a higher level interface, to create a new model and test it with different parameters. And it's really the recommended solution for beginners. And it also does allow for fast computation and acceleration using GPUs. And there is many examples you can find online on the website, as well as in the general community. An alternative is PyTorch, which is a slightly higher level machine learning library compared to TensorFlow. And it's well optimized for very fast input and output of data, and for quite demanding tasks that requires lots of hardware and implementation of your models for multi-GPUs. So this could be potentially useful if you really have a demanding project. But for this quick tutorial, we would recommend the TensorFlow and Keras as the beginning step.
Welcome to the second part of this video. This will be a short tutorial on Jupyter Notebook that covers how to check that TensorFlow is running on the GPU, how to import medical images, how to define training, validation, and test sets, how to define and train a simple 3D CNN, and finally, how to save the results. In this short tutorial, the dataset that will be used for training is composed of simulated 3D PET images and their corresponding labels. So the labels are ground truth images without noise and partial volume effect. The aim of this regression network is to recover the original activities from the reconstructed PET images. The goal of this tutorial is to show you a working pipeline for deep learning. The CNN will not be optimized to yield the best performance. In order to run a cell, we will click on the relevant cell and then on the run command. In the first cell, the relevant packages will be imported. Subsequently, two functions will be defined. The first one is called plot 2D slices, and it allows to plot selected 2D slices from a 4D or 5D matrix. The first dimension will always be the number of samples in our dataset. The next three dimensions will contain the 3D data belonging to each sample. The fifth dimension, which is optional, contains the number of channels, which in our case is 1. The second function defined here is called open and reshape. It allows to open .img files and reshape them to the wanted dimensions. In deep learning, the datasets used for training are usually large. Thus, it is convenient to run the program on a GPU. In this case, we have installed Tensorflow GPU using Anaconda, as explained previously in this video. The following commands will allow us to check that Tensorflow has access to the GPU, which in here is called device 0. We now test that Tensorflow has been built with GPU support, and you can see here that in our case, it is true. We are now ready to import our dataset. At first, we need to define the folders in which the data are stored. In this case, the data are stored in the input data folder, and the results will be saved in the output data folder. Any plot in this script will be saved in the output plots folder. We now want to define some variables that will be used later. The first three variables represent the dimensions of the training samples. In our case, they will be 50 by 50 by 50 voxels. The third variable defines the number of channels of the images. In our case, it is 1. The reconstructed paired images and corresponding labels are then loaded from the previously defined folder using the glob function. And in this tutorial, we will only use 10 samples to train and test our workflow. Usually, thousands of samples are used for training. The file name of our dataset will be stored in a list and will be used later when saving our results. In the next cell, the loaded .img file will be opened and reshaped to the correct size. The final matrix dimensions will be printed to check that they are correct. We can also plot some 2D slices belonging to the label images and to the corresponding reconstructed paired images in order to check that the two volumes match and that the matrices have been correctly reshaped. The training and test datasets will now be defined using the train test split function. We will also use a list of indexes called IDX to keep track of how the input data is reshuffled and split into training and testing datasets. Having defined the training and testing datasets, we can now define the CNN architecture. In this example, our simple 3D CNN is composed of 4 convolutional layers, each followed by a batch normalization layer, except for the last one. We now need to compile the CNN and choose the optimizer. In our case, we chose to train with the Adam optimizer. And we also need to choose the loss function, which in our case will be mean squared error. The summary function will yield a summary of the structure of our network, together with the number of parameters in each layer. We can finally train the CNN. The batch size and number of epochs need to be defined before training. We will only train for 10 epochs in this tutorial. The CNN is trained using the .train function, which allows to define a ratio of data that will be used for validation. In this case, we have set it to 0.2. As you can see, at each epoch, the script outputs the values of the training and validation loss. When training has finished, it is possible to plot the loss function against the number of epochs. This plot is very helpful to check that the network has or hasn't reached convergence, and it gives an indication of how many epochs will be needed to train the network. In this case, you can see that the values are very high because we are using very few samples and we are training for very few epochs. We can also plot the we can also print the accuracy scores, which also can help to assess the performance of the network. Finally, we can test the network on the test dataset. We will use the predict function for this and apply it to two volumes that were not used for training. We can plot a range of 2D slices belonging respectively to test labels, then reconstructions, and predicted images to check, for example, that the shapes match. Finally, the data will be saved in .img format. We hope you enjoyed this short tutorial and that you will check out our next videos. Bye!